Deep warming, the climate problem that both post and predates greenhouse emissions. In 1998, a team led by physicist Martin Hoffert of New York University concluded the Earth's atmospheric carbon dioxide content cannot be stabilized without a tenfold increase in carbon emission-free power generation over the next 50 years. 7 years later, Richard Smalley, Nobel laureate in chemistry, determined that, to give all 10 billion people on the planet the level of energy prosperity we in the developed world are used to, a couple of kilowatt hours per person, we would need to generate 60 terawatts around the planet. These goals, however, run up against the thermodynamic limits identified by physicists Tom Murphy, Mark Buchanan, and others like Mark Flanner and Eric Chason, who refer to the problem as deep warming, or as simply waste heat. This byproduct of all thermal processes that produce energy and the low thermodynamic efficiency of these processes are unsustainable and are largely underestimated. The 2015 Guardian article, Nuclear Power Paves the Only Viable Path Forward on Climate Change, by 4 of the world's most respected climate scientists asserts, to solve the climate problem, policy must be based on facts and not prejudice. Alongside renewables, nuclear will make the difference between the world missing crucial climate targets or achieving them, they claimed. With respect to facts and prejudices, however, the first principle of climate change is, it is a problem of thermodynamics, and there is a scientific bias against an ocean-centric solution to the problem of global warming. A rebuttal letter in The Guardian by 4 other scientists says, contrary to the original article, many scientists around the world remain skeptical that nuclear is the answer, or even part of the answer, to climate change. Acknowledging that the original authors have a fine record in identifying the causes and consequences of climate change, their proposed solution simply doesn't make sense, assert the refuters. The main problem is that, contrary to what many think, nuclear power is a poor method of reducing carbon emissions. Its uranium ore and fuel processes have heavy carbon footprints. Indeed, of the ways to reduce carbon emissions in the energy sphere, renewables, especially wind and solar, are now less expensive, quicker to install, and much safer. With them, one does not have to worry about the specters of Chernobyl and Fukushima, they assert. But perhaps most important of all is the moral dimension. Given the technical and political obstacles to dangerous spent nuclear fuel, should we be passing these problems to future generations? In support of the latter assessment, Professor Mark Jacobson of Stanford has pointed out, the only nuclear plant currently being built in the United States is costing 15 times current wind and solar costs, produces 9 to 37 times more carbon dioxide and pollution per kilowatt hour than wind. It is taking between 17 to 19 years between planning and operation compared to the half to 5-year lead time for wind and solar. As weapons proliferation, meltdown, waste, and mining risks. And the alternative fusion power is being touted by some as the energy holy grail that can save us from the climate crisis. But, since what we do about carbon emissions in the next 2 or 3 decades is likely to determine whether the planet gets just uncomfortably or catastrophically warmer by the end of the century, then fusion won't be our salvation. The problem of waste heat far predates either global warming or our current energy dilemma and will be with us much longer. Waste heat could radically alter Earth's future, Mark Buchanan, a physicist, science writer, and former editor at Nature and New Scientist, noted in the EON article, Deep Warming. As far back as 1965, scientists from the U.S. government warned that the use of fossil fuels would cause global warming, with potentially disastrous consequences for Earth's climate. In the paper Time Scales and Ratios of Climate Forcing Due to Thermal versus Carbon Dioxide Emissions from Fossil Fuels, Zhang and Caldera demonstrated that the Earth warms both when fossil fuel carbon is oxidized to carbon dioxide and when the greenhouse effect of carbon dioxide inhibits long-wave radiation from escaping to space. These are 2 different climate forcings, with 2 different time scales. The radiative forcing from burning of fossil fuel exceeds the heat released upon combustion within 2 months. But over the lifetime of the carbon dioxide in the atmosphere, the cumulative radiative forcing exceeds the amount of energy released upon combustion by a factor greater than 100,000. As Yi Tao of Harvard's Roland Institute warns, temperature rise is the biggest and gravest concern that we face. We are overstepping a heat threshold, he cautions. That threshold is the thermodynamic limit. Tom Murphy, professor of physics, University of California, San Diego, demonstrated in his article Galactic Scale Energy from his series Do the Math. Murphy showed that since 1650, America's energy usage has steadily climbed at the logarithmic rate of 2.9% per year. This viral rate of growth leads to a requirement for all the solar energy that strikes the Earth within the next 400 years. And in a third graphic shows the thermodynamic implications of that kind of temperature rise. We confine ourselves to the Earth's surface, we exhaust solar potential in 400 years. So in order to continue energy growth beyond that time, we would need to abandon renewables, virtually all of which derive from the sun, for nuclear fission or fusion. But the thermodynamic analysis says by that time we will be toast in any case. Gavin Schmidt, a climate modeler working for NASA with Columbia University, points out, for obvious reasons, we are interested in how the climate system will respond to an increase in CO2, which depends on timescale and what feedbacks we consider. The Charney sensitivity is generally thought of as the medium-term response of the system, including all the fast feedbacks and some of the longer-term ones, like the ocean. This is usually what is meant by climate sensitivity in normal conversation. On longer, multi-millennial timescales, we expect changes in vegetation and ice sheets to occur and alter the response, and that sensitivity is often described as the Earth system sensitivity. This is a multi-millennial proposition, but as Murphy shows, mankind doesn't have multi-millennia. In 450 years at our current rate of consumption of energy, the surface will be hot enough to boil water. 50 years later, it will be hot enough to set paper on fire. Slightly over 2 centuries after that, it will be hot enough to melt steel. And 2 centuries after that, about 1,000 years from now, the Earth's surface will be as hot as the surface of the sun. A logarithmic scale of energy usage, however, is deceptive. A linear scale shows energy usage in a more instructive light. In 1650, the global population was about 500 million, and a single individual can produce about 75 watts a day. So global usage for 1 year would have been about 0.00004 terawatts. This linear scale graph from 1650 to 3023 with an energy accelerator of 2.6% shows that by 3023 the global energy usage would be 81 billion terawatts, whereas only 79,000 terawatts actually heat the Earth's surface each year. Albert Einstein considered thermodynamics amongst those principles unlikely to be changed by future scientific discoveries. It is the only physical theory of universal content, he wrote, concerning which I am convinced that within the framework of the applicability of its basic concepts, it will never be overthrown. Yet we simply disregard these basic concepts at our peril. The power of thermodynamics rests on the understanding that fundamental consequences follow from how the energy is organized within a system, as reflected in its entropy, which is a measure of the molecular disorder, or randomness, of the system. All the energy we consume ends up as heat in the environment, but to a small degree, the physical changes we make in the conversion of raw materials into finished goods and infrastructure. But most of the heat we consume is turned to waste heat, which is a direct consequence of the laws of thermodynamics. The first law of thermodynamics states that the total quantity of energy never changes but is conserved. Energy, in other words, never disappears but can change form. The second law of thermodynamics states that, in natural processes, the transformation of energy always moves from more organized and useful forms to less organized and less useful forms. In other words, we are constantly generating waste heat with everything we do. Mark Flanner, a professor of Earth System Science at the University of California at Irvine, in a paper integrating anthropogenic heat flux with global climate models, says this flux is neglected in current global climate models because, globally, it averages only about 1% of greenhouse gas forcing, but as this worksheet shows, at only 1% exponential growth, it only takes 444 years for today's waste heat flux to amount to the same flux as today's carbon dioxide emissions. One of the first people to describe the problem of waste heat in 2008 was the Harvard astrophysicist Eric Chason, who discussed the issue in a paper titled Long-Term Global Heating from Energy Usage. He concluded that our technological society may be facing a fundamental limit to growth due to the unavoidable global heating dictated solely by the second law of thermodynamics. Energy use always ends up as heat. How this happens is described by the laws of thermodynamics, which were described in the mid-19th century by scientists including Sadi Carnot in France and Rudolf Clausius in Germany. Chasen said avoiding or delaying deep warming will involve slowing the rise of waste heat, which will entail restricting the amount of energy we use and also choosing energy sources that exacerbate the problem as little as possible. Thermodynamic geoengineering, however, offers energy that, instead of producing waste heat, stores trapped solar heat not converted to work in the ocean until such times as it becomes available again to produce more work. And instead of restricting the amount of energy we use, the more energy that is produced with this solution, the more the ocean's surface, and by extension the rest of the planet, is cooled. Unlike the energy from fossil fuels or nuclear power, that adds to our waste energy burden, renewable energy sources intercept energy that is inexorably on its way to Earth, rather than producing additional waste heat. In this sense, the deep warming problem is another reason to pursue renewable energy sources such as solar or wind, rather than alternatives such as nuclear fusion, fission, or even geothermal power. If we derive energy from any of these sources, we're unleashing new flows of energy into the Earth system without making a compensating reduction in energy usage. As a result, all such sources will add to the waste heat problem. However, if renewable sources of energy are deployed correctly, they need not add to our deposition of waste heat in the environment. In fact, thermodynamic geoengineering eliminates waste heat and global warming by converting the heat of warming to work and sending the so-called waste heat into the deep, where it can diffuse back to the surface in 226 years, at which it can be recycled until all of the heat of warming has been converted to work, and the waste heat of those conversion is dissipated to space. By using this energy, we produce no more waste heat than would have been created by sunlight in the first place, Mark Buchanan says in the EON article. So it boils down to a matter of which renewable energy source is most abundant, costs the least, has the highest capacity, has the lowest surface footprint, and provides the most environmental benefit. Mark and Richard Perez partially addressed this in their paper, Update 2022, A Fundamental Look at Supply-Side Energy Reserves for the Planet. The 175,000 terawatts per year of solar energy hitting the Earth's surface annually constitutes the largest readily accessible energetic resource available on Earth and the source from which most other, notably fossil fuels, energy sources are derived, they say. Through the lens of reasonably assured recoverable reserves, they compared the percentage of this solar energy that can be converted to usable energy, as in electricity, to the potential of other renewables like wind, hydroelectric, geothermal, ocean thermal, wave tides, biomass, and conventional non-renewable reserves like coal, oil, gas, nuclear, and primary demand. And found that solar photovoltaics are capable of meeting 100% of extant global primary energy demand, more than 12 times over, and wind 2 times over even after reasonable constraints posed by land use and conversion efficiency are considered. Under a fully electrified future scenario, solar power could meet global energy demand 27 times over, and wind 5 times over, they say. The U.S. National Renewable Energy Laboratory has determined that the total useful wind farm requires about 250,000 square meters of surface area to produce 1 megawatt of power. And the total land required for 1 megawatt of photovoltaics is about 16,000 square meters. As an alternative, a 1 gigawatt thermodynamic geoengineering plant would graze the tropical ocean surface using only 43,000 square meters of ocean real estate to produce electricity that can decarbonize every sector of the global economy on green fields that would cover about 273,000 square meters. For example, magnesium, which has ideal properties for heat exchangers like those used by the technology, exists in the ocean at a concentration 3 times higher than carbon dioxide exists in the atmosphere. Lazard Limited, the financial advisory and asset management firm, assess wind and solar as the cheapest of the energy sources on a levelized cost of energy basis. But levelized cost does not account for time effects associated with matching electricity production to demand, nor dispatchability, which is the ability of a generating system to come online, go offline, or ramp up or down quickly as demand swings. MIT's Jessica Transick estimates to provide baseload, intermediate, bi-peaker, and peaker electricity at 10 cents a kilowatt-hour with an optimal wind-solar mix, energy storage capacity costs must reach approximately $30 to $70 a kilowatt, or 3 to 7 times the cost of the energy. After wind and solar, the Pharisees ranked geothermal and biomass as the next most abundant energy sources, both of which must be ruled out on account of their potential to produce waste heat. Which leaves ocean thermal energy conversion, which is base load power, of which thermodynamic geoengineering is the most efficient iteration. The Perez's state that the global potential ocean thermal energy conversion is of the order of 30 terawatts per year. But its economic potential is unknown as it is still an immature technology with no commercial plant operating. This assessment was for conventional OTEC that is 39% as efficient as thermodynamic geoengineering, half again as expensive and produces 39% as much energy. And at the gigawatt scale can cost about 1.1 cents per kilowatt hour and requires no storage. In part, this is because it has the highest energy capacity of all of the energy options. 30 years ago, there was no such thing as a smartphone, but that didn't stop IBM from inventing one and starting a communications revolution. That is about the length of time that is required to create a waste heat-free future, and the energy revolution that will provide the cheapest and most benign energy.